This is section 2.4, velocity and other rates of change. Here we have the formal definition of derivative, but it's also the instantaneous rate of change or the instantaneous velocity. Example 1, enlarging circles. A, find the rate of change of the area of a circle with respect to its radius r. So A is equal to pi r squared. And we're finding the rate of change, so we're going to take the derivative. A prime is equal to 2 pi r. B, evaluate the rate of change of A at r equals 5 and r equals 10. So A prime of 5 is equal to 10 pi, because we're going to plug 5 into r. And A prime of 10 is equal to 20 pi. See if r is measured in inches, A is measured in square inches. What units are appropriate for dA dr? Well, that would be inches squared per inch, and labels don't cancel, so we can't cancel this to be just inches. Acceleration is the derivative of velocity with respect to time. If a body's velocity at time t is v of t equals ds dt, then the body's acceleration at time t is the second derivative. So we have the position function. Then if position changes, that's velocity. So the derivative of the position function is the velocity function. And then if velocity changes, that's acceleration. So the derivative of velocity is equal to acceleration. So the acceleration is the second derivative of the position function. Now, the position function, if you want to have gravity be 32 feet per second squared, then you start with 16t squared, because then velocity would be 32t and acceleration would be 32, and you would get that 32 feet per second squared. And in the metric system, it'd be 4.9 t squared for the position function. Modeling vertical motion. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of 160t minus 16t squared feet after t seconds. A, how high does the rock go? Well, we know that the rock has reached its maximum height when the velocity is 0, because it's going to go up, it's going to stop, and then it's going to come back down. So velocity is equal to 160 minus 32t. And we want to know when that's 0. So we add 32 over, divide by 32, and we get 5 seconds. Letter B, what are the velocity and speed of the rock when it is 256 feet above the ground on the way up and on the way down? Well, 256 feet is position, so we're going to plug that in for S. So 256 is equal to 160t minus 16t squared. Let's add 16t squared and minus 160t. Minus 160t, and we have plus 256. That's equal to 0 now. We're going to factor out a 16. So if t squared minus 10t plus, I think that's 16, equals 0. And then this factor is t minus 4, and no, actually t minus 2, and t minus 8. So t equals 2 and t equals 8. But they want the velocity and the speed on the way up and on the way down. So let's go with velocity on the way up. That's we're going to plug 2 in for the velocity function. So v of 2 is equal to 160 minus 32 times 2. That's 160 minus 64. So that's 96 feet per second. The speed on the way up is equal to 96 feet per second. Speed is always positive, so we just take the absolute value of the velocity. Velocity has direction, speed does not. Then we have velocity coming down now. V of 8 is equal to 160 minus 32 times 8, and that's negative 96 feet per second. So the speed coming down is equal to 96 feet per second, because speed is the absolute value of velocity. Letter C, when is the acceleration of the rock at any time t? What is the acceleration at any time t? So we're going to do the derivative of velocity is acceleration. So the acceleration is negative 32 feet per second squared. And the reason it's negative is because gravity pulls down. So up is positive, down is negative. So letter D, when does the rock hit the ground? Well, that's when the position function is going to be 0. So 0 is equal to 160t minus 16t squared, and we're going to factor out a 16. That's 10x 16t. 10 minus t, and so t equals 0 means it starts on the ground, and then it ends its flight at 10 seconds. Studying particle motion, a particle moves along a line so that its position anytime t greater than or equals 0 is given by the function this, where s is measured in meters and t is measured in seconds. So this is the position function. Letter A, find the displacement of the particle during the first 2 seconds. So that's going to be s of 2, where it ends up, minus where it started, which would be at 0 seconds. So that's equal to 4 minus 8 plus 3 minus, if I plug a 0 into the position function, that's just going to be 3. So its displacement is negative 4, which means it's 4 to the left of where it started. Find the average velocity of the particle during the first 4 seconds. We need s of 4 minus s of 0 over 4 minus 0. So let's plug 4 in. That's 16 minus 16 plus 3. When we plug 0 in, that's going to be minus 3 over 4, and both those are going to cancel out, so we get 0 over 4, which ends up being 0. And I guess we need some labels here. The first one is meters. This is velocity, average rate of change. So that's going to be meters per second. Letter C, find the instantaneous velocity of the particle when t is equal to 4. So the velocity is equal to 2t minus 4. And they want v of 4. So 8 minus 4 is 4 meters per second. Letter D, find the acceleration of the particle when t is equal to 4. Well, acceleration is the derivative of velocity, so that's just going to be 2 meters per second squared. Letter E, describe the motion of the particle. At what value or values of t does the particle change direction? So the way that we're going to describe the motion is a little different than what the book does. We're going to say where the particle is stopped, where it's moving to the right, and when it's moving to the left. Now we know it's stopped when the velocity is 0. So 0 is equal to 2t minus 4, add 4, divide by 2. So when stopped when t is equal to 2. Now we're going to put this velocity on a number line, so 2. And we're starting at 0, so let's plug 1 into the velocity. 2 minus 4 is negative 2, so the velocity is negative from 0 to 2. That means this particle is moving to the left, 0 to 2. Then when we plug 3 in, 6 minus 4 is positive, so now if the velocity is positive, then this particle is moving to the right. So 2 to the infinity, particles moving to the right. Letter F, use parametric graphing to view the motion of the particle on the horizontal line. And let me open a calculator. We're going to put this into parametric mode. And we'll have y equals. Let me clear this out of there. And we need the position function to see the motion. So we have t squared minus 4t plus 3. And we're on the line y equals 2. So y equals 2. And if you go up here and select This one, you can see the motion. So zoom 6. So there's the first 2 seconds, and then it particle goes to the right after that. Write the area of a circle as a function of the circumference. So letter A, area equals pi r squared, and circumference equals 2 pi r. So we want to write the area in terms of the circumference. So r is equal to c over 2 pi, and we're going to plug this in for r. So a is equal to pi times c squared over 4 pi squared. The pi's cancel out, and we have c squared over 4 pi. Letter B, find the instantaneous rate of change of the area A with respect to the circumference C. So A prime is equal to 2 over 4 pi times C, which ends up being C over 2 pi. Letter C, evaluate the rate of change of A at C equals pi and C equals 6 pi. So A prime of pi is equal to pi over 2 pi, which is 1/2. And then A prime of 6 pi is equal to 6 pi over 2 pi, which is 3. Letter D, if C is measured in inches and A is measured in square inches, what units would be appropriate for DADC? And that'd be inches squared per inch. Labels don't cancel. A square of side length S is inscribed in a circle of radius R. So let's draw a circle, and the square is inscribed. That means this diagonal of the square is 2 times the radius. This is 2r. There's a side of the square. There's a side of the square. We're going to write the area of the square as a function of the radius. So the area of a square is side squared. And here we have s squared plus s squared is equal to 4r squared. That's Pythagorean theorem. So 2s squared is equal to 4r squared. So s squared is equal to 2r squared. And we're going to square root. So s is equal to r times the square root of 2. Now when we square this, because we're going to plug that in for s, we get 2r squared. So there's letter A. B, find the instantaneous rate of change of the area A with respect to the radius r of the circle. So letter B, A prime is equal to 4r. Letter C, evaluate the rate of change of A at r equals 1 and r equals 8. So A prime of 1 is 4, and A prime of 8 is equal to 32. Letter D, if r is measured in inches and A is measured in square inches, what units would be appropriate? Again, inches squared per inch would be the label for that. The number of gallons of water in a tank t minutes after the tank has started to drain is Q of t. Q of t is the position function. How fast is the water running out at the end of 10 minutes? All right, so let's write Q of t like this, multiply it out. 200 times 900 minus 60t plus t squared. And let's run the 200 through. So we get 18 with 4, 180,000 minus 12,000 t plus 200 t squared. So that's Q of t. That's still the position function. And it says how fast is the water running out at the end of 10 minutes. So we want, that's not Q prime, that's just Q. So Q prime of t is equal to negative 12,000 plus 400 t, t. Now we're going to evaluate that when t is equal to 10, which is negative 12,000 plus 4,000. So that's going to be negative 8,000, and we're going to go with gallons per minute. So gallons per minute. What is the average rate of change at which the water flows out during the first 10 minutes? Well, average rate of change is going to be q of 10 minus q of 0 over 10 minus 0. So let's plug those values back into the original. That's probably the easiest place to do that. So we have 200 times 20 squared minus 200 times 30 squared over 10. And that's equal to 200 times 400 minus 200 times 900 over 10. And we could do it like this. We could go 200 times negative 500 over 10. And negative 10, 1, 2, 3, 4 over 10. And finally, negative 10,000 gallons per minute, I think it is. Yep, gallons per minute. A particle P moves on the number line shown in part A of the accompanying figure. Part B shows the position of P as a function of time t. So this graph is the position graph. Letter A, when is P moving to the left? So left is going to be where the slope is negative, because that's the velocity. So 2 to 3 and 5 to 6. So 2 to 3 and 5 to 6. Moving to the right. That's where the slope is positive. So 0 to 2. And standing still. So stopped. That's going to be 1 to 2 because the position isn't changing. It's staying 2. So 1 to 2. And then 3 to 5. Graph the particle's velocity and speed. So the velocity is the slopes of all the tangent lines. So from 0 to 1, we would plot 1. And then from 1 to 2, we'll plot 0. And then 2 to 3, down 2 and over 1, that's negative 2. So negative 2. 3 to 5 is 0. And 5 to 6 is down 2 over 1, negative 2. Over here, let's see. Up 2 over 1, that's 2. So this is wrong right here. It's actually up here, like that. So there's the velocity. Now the speed is the same thing, except anywhere this is negative, it goes up to being positive. Because speed's always positive. So that stays there. And then this one is going to go up to 2 right there. The graphs in figure 2.33 show as functions of time t the position s. The velocity v equals dst/t, and the acceleration a equals the second derivative of a body moving along a coordinate line. Which graph is which? Give reasons for your answer. Well, this is the position function, and we see that the slopes are always negative. And this graph is always negative, so this must be the velocity, because it's the derivative of the position function. And then the slopes change from being negative to being positive, and this curve changes from negative to positive, so this must be the second derivative, or the acceleration.